Okay, so here's the problem we were working on previously, and I think it stumped us a little bit because there was lots of redrawing we had to do, but particularly with these areas that were very confusing as to what we should do, because it's not clear whether or not they are series or parallel, or in what order we should be doing things. So what we're going to end up doing with this is we're going to redraw it to make it much simpler so that it's more apparent what order we should do things in. Okay, so whenever we're reducing circuits, it's not always clear what order we should go at to reduce the circuits. For instance, for this one, would we be better off reducing these as parallel first, or these as series first, or these as series first? It's not apparent at first glance. So what we can do is we can redraw a circuit so that it's more apparent in the redrawn state what order we should go at. So to help us imagine this, we're going to uncurl our circuit. So if here's our cell, we're going to go ahead and make this our long post, and we'll put our short post over here. Okay? So what we're going to do is we're just going to run this along in a straight line, and then we'll hit our first resistor right here, resistor 1. So we'll just draw that in over top. Now we'll go a little bit further, and now we come up and around, and we meet a point where we have a split, right? So what we're going to do is we're going to draw all of our splits like that, like this. We're just going to draw a line down and draw one going in each direction. So let's go ahead and do the top one, which we'll say is this leg of the circuit. So going along the top, we reach resistor 2. So we'll go ahead and draw that in. And then we go a little bit further, we reach resistor 3. And then it recombines. So we'll go ahead and bring that down. And then we go over the other way, we reach resistor 4, and it recombines. Now we will just go ahead and take this to the short end of the cell, and it's a little simpler this way to see what order we should do things. We know we can't do this as parallel yet because we need to do this as series first. Once we have this reduced, we'll be able to do this in parallel, and once we have that reduced, we would be able to do this in series. And this will directly correspond to this circuit. And so if this linear layout doesn't work, another way that we can think about redrawing our circuits is to make our junctions a little easier, is to bring it down and to make two branches at every parallel. So we'll go ahead and draw in resistor 1 before our split. Now we know there's a split here, so we're going to come down and draw our T shape again, and we'll know that there's a line coming down, and then they'll recombine, right? So here's where we will put R2, R3, and then R4. They will recombine here, and we'll take them over and complete our circuit. Let's go ahead and draw our cell. And then the first resistor is pretty straightforward. This will stay the same. Just going to draw that in. And we're going to bring this over, and we had two main branches or legs coming down like this. Go ahead and draw those in, and we'll draw the resistor that was up here in between the two. All right, this was our 1 ohm, and here is our 2 ohm resistor. Okay, so this initial part over here, we're going to go ahead and redraw this so that it's more apparent what is series and what is parallel. So here we're going to put our two resistors in series. These will be the two 0.5 ohm resistors. And then over here we will put the 2 ohm resistor. You can see immediately from redrawing this that these are obviously in series, and then whenever we reduce these to a single resistor, it'll be in parallel with the resistor opposite to it, and we'll have a parallel that we can reduce. Coming over here, we have a little bit more difficult of a setup. We're going to go ahead and do 2 branches from here, and then we're going to bring this down. We're going to do 2 branches from here. So here we have a set of parallel. So we're going to draw these in, combine at the bottom. We're going to have, here will be our 0.5 ohm resistor, and then over here will be our 1 ohm resistor. And these will recombine, and we'll have our 0.5 ohm resistor, And then this bottom line, we're just going to take all the way over, because this will be the bottom of our circuit. Okay? Now for this branch, we're just going to have one single set of parallel. So bring this over, and then we'll recombine them like this. And drag these down. And then here we have another set of parallel, which will be, here's our 2 ohm. And then here will be our 1 ohm. So here it's a little more obvious what steps we're going to take, because everything's a little bit more self-explanatory. For example, we know that these are going to be parallel, so we'll be able to combine these using the parallel equation. Same with these. We know that these are series, but then we'll get a parallel, and we'll be able to reduce those. Okay, so what we're going to do here is these 2 resistors right here are in series, right? So we should be able to add these using our series equation. So our series equation, we're going to say our resistance is going to be equal to R1 plus R2, right? And this is going to be equal to 1/2 ohm plus 0.5 ohms, which this will give us an equivalent resistance of 1 ohm. So we're going to reduce these 2 series resistors into a single resistor. So using this, we'll just put a single ohm resistor along here, and this will be 1 ohm. Alright, now we're going to reduce these 2 resistors down to a single resistor. To do this, we're going to use the parallel resistor formula. So we're going to have 1 over R is equal to 1 over R1 plus 1 over R2. This is going to be equal to 1 over 2, which is that resistor, plus 1 over 1. This will give us, if we go ahead and multiply this by 2 so that the denominators are the same, we'll get a 2 over 2. Now we add the 1 and the 2 together, and we'll have a 3/2. Alright, now we have a 1 over R is equal to a 3/2. So we'll invert both sides, and that will give us R is equal to 2/3. Now we're going to go ahead and put this equivalent resistor into our circuit. So let's erase our 2 parallel. We'll draw a straight line down, and we'll add our equivalent resistor, which we'll say is 2/3 ohms. Okay, so now we can go ahead and follow this same equation to find the next parallel. So the next parallel we're going to work with will be this set. So we're going to have another 1 over 1 plus a 1 over 2. We're going to follow the same method as before, where we're going to change this to a 2 over 2. This will give us another 3/2. We'll have our 1 over R is equal to 3 over 2. So whenever we inverse both sides, we get R is equal to 2/3 again. We'll go ahead and erase this and plug that in. Okay, so now we're going to combine these 2 parallel resistors. Okay, we're going to have a 1 over 0.5 plus a 1 over 1. Okay, we're going to get this denominator the same as the denominator for the 1 over 1. To do that, we're going to multiply it by 2. So we can rewrite this as a 2 over 1. So we have a 2 over 1 plus a 1 over 1. This is going to give us a 3 over 1. I'm going to go ahead and say 1 over R is equal to 3 over 1. So we'll inverse both sides, and we'll get R is equal to 1/3 ohms. So now we can go over here, and we can erase the parallel and put a single resistor in that is the combination, and it'll be 1/3 ohms. Okay, now we can look at this and we can see that these 2 are in series. So we'll go ahead and take these out real quick. So 1/3 plus the 0.5 Okay, so I went ahead and rewrote this as 1 over 2 to make our fractions a little bit easier. So we're going to have 1/3 plus 1/2. All right, we need a common denominator. We'll go ahead and say 6. So that means we're going to multiply this by 2, and we're going to get 2/6 plus, we're going to multiply the 1/2 by 3. We're going to get 3/6, and that'll give us a total of 5/6. All right, and this will be in ohms. So now we can erase this and put in an equivalent resistance here. So looking at this, the next step to do will be to go ahead and combine these two resistors in parallel. Okay? So we're going to go ahead and say 1 over R. This will be 1 over 2/3 plus 1 over 5/6. Now, this is essentially taking the inverse like we did earlier. So we can actually just flip these around. This will be equal to 3/2 plus 6/5. So now we're going to have a common denominator to add these two. So we'll go ahead and use our common denominator of 10, which means that this will be equal to 15/10 plus 12/10, which gives us 27/10. And this will be 1 over R. So to get the resistance, we'll have to take the inverse, draw our little arrow. We'll say R is equal to 10 over 27. So now we can erase this and plug that in. So for right here, we can see that even though these are not one right after the other, they are in series because the same wire runs through them both, right? So we're going to go ahead and plug these in as series. We're going to combine them as series. So we're going to say R equals 2 plus 10/27. Okay? So if we put 2 in terms of 27ths, I'm going to say that this is equal to 54/27 plus 10/27, and that is equal to 64/27. So here, it may look like we want to do a series, but we still don't want to do the series yet. We want to tackle this parallel, and then our series will be with the 1. So we're going to go ahead and tackle this parallel resistors. Now we can do what we did earlier, and we can go ahead and flip these since these are inverses. So we'll have 3/2 plus 27/64. Okay, so to get the same denominator, we're going to multiply our 3/2 by 32 so the denominators are the same. So we'll get 96/64 plus 27/64. And this is equal to 123 over 64. And that will be, this is the 1 over R. So we'll still have to flip that upside down, and we'll get R equals 64 over 123. And so now we just have one last series. We'll have the 1 in series with the 64 123rds. So we'll combine these in series. So we'll have R is equal to 1 plus 64 over 123. All right, get this in the same common denominator. We can imagine this as 1 over 1, which will give us Let's just go ahead and rewrite that here. 1 over 1, it could also be 123 over 123. So we're going to add 123 to 64. That's going to give us 187 over 123 ohms. So we can redraw this as our single resistor circuit is 187 over 123 ohms, and that comes out to about 1.52 ohms. So we were able to solve a pretty complex circuit by redrawing it, and it became more apparent what order to do the reductions in. So if we do encounter another more difficult circuit, the first step that we should do is we should always redraw the circuit so that we know what order to do things in.